Purification of Organic Compounds by Crystallization using Solvents. Aim: recrystallization of given organic compound with suitable solvent like water, alcohol, acetone, etc. Apparatus. Procedure: recrystallization is a technique used to purify solid compounds. Solids tend to be more soluble in hot liquids than in cold liquids. During recrystallization, an impure solid compound is dissolved in a hot liquid until the solution is saturated, and then the liquid is allowed to cool. The compound should then form relatively pure crystals. Ideally, any impurities that are present will remain in the solution and will not be incorporated into the growing crystals. Figure 1. The crystals can then be removed from the solution by filtration. Not the entire compound is recoverable, some will remain in the solution and will be lost. Recrystallization is not generally thought of as a separation technique. Rather, it is a purification technique in which a small amount of an impurity is removed from a compound. However, if the solubility properties of two compounds are sufficiently different, recrystallization can be used to separate them, even if they are present in nearly equal amounts. Recrystallization works best when most impurities have already been removed by another method, such as extraction or column chromatography. Figure 1. The general scheme for recrystallization. Principle: a successful recrystallization depends on the proper choice of solvent. The compound must be soluble in the hot solvent and insoluble in the same solvent when it is cold. For the purpose of recrystallization, consider 3% W/V the dividing line between soluble and insoluble. If 3G of a compound dissolves in 100 ml of solvent, it is considered soluble. In choosing a solvent, the bigger the difference between hot solubility and cold solubility, the more product recoverable from recrystallization. The rate of cooling determines the size and quality of the crystals. Rapid cooling favors small crystals, and slow cooling favors the growth of large and generally purer crystals. The rate of recrystallization is usually greatest at about 50 degrees Celsius below the melting point of the substance. The maximum formation of crystals occurs at about 100 degrees Celsius below the melting point. Although the terms crystallization and recrystallization are sometimes used interchangeably, they technically refer to different processes. Crystallization refers to the formation of a new insoluble product by a chemical reaction. This product then precipitates out of the reaction solution as an amorphous solid containing many trapped impurities. Recrystallization does not involve a chemical reaction. The crude product is simply dissolved into solution, and then the conditions are changed to allow crystals to reform. Recrystallization produces a more pure final product. For this reason, experimental procedures that produce a solid product by crystallization normally include a final recrystallization step to give the pure compound. Procedure: perform all steps in a fume hood to prevent exposure to solvent fumes. Selecting a solvent, place 50 mg of the sample, N-bromosuccinimide, in an Erlenmeyer flask. Add 0.5 ml of boiling solvent. Water. If the sample dissolves completely, the solubility in the cold solvent is too high to be a good recrystallization solvent. If the sample does not dissolve in the cold solvent, heat the test tube until the solvent boils. If the sample has not completely dissolved at this point, add more boiling solvent dropwise until all of the solid dissolves. If it takes more than 3 ml to dissolve the sample in the hot solvent, the solubility in this solvent is probably too low to make it a good recrystallization solvent. If the first choice of solvent is not a good recrystallization solvent, try others. If a single solvent that works cannot be found, try a two-solvent system. If you cannot find a suitable single solvent system, then a solvent pair may be necessary. When identifying a solvent pair, there are several key considerations. The first solvent should readily dissolve the solid. The second solvent must be miscible with the first solvent, but have a much lower solubility for the solute. As a general rule, likes dissolve likes, meaning that polar compounds tend to be soluble in polar solvents, and nonpolar compounds are often more soluble nonpolar compounds. Common solvent pairs, Table 1, Make sure the solvent has a boiling point of at least 40 degrees Celsius, so there is a reasonable temperature difference between boiling solvent and room temperature solvent. Ensure that the solvent has a boiling point below about 120 degrees Celsius, so it's easier to remove the last traces of solvent from the crystals. Also make sure the boiling point of the solvent is lower than the melting point of the compound, so the compound forms as solid crystals rather than as an insoluble oil. Confirm that the impurities are either insoluble in the hot solvent, so they can be hot filtered out once the compound is dissolved, or soluble in the cold solvent, so they stay dissolved during the entire process. This is a better choice than a beaker, since the sloping sides help trap solvent vapors and slow the rate of evaporation. Place the solvent water in a separate Erlenmeyer flask and add boiling chips or a stir bar to keep it boiling smoothly. Heat it to boiling on a hot plate. Add hot solvent to a flask at room temperature containing the compound in small portions, swirling after each addition until the compound is completely dissolved. During the dissolution process, keep the solution hot at all times by resting it on the hot plate too. Do not add more hot solvent than necessary, just enough to dissolve the sample. If a portion of the solid does not seem to dissolve, even after more hot solvent has been added, it is likely due to the presence of very insoluble impurities. If this happens, stop adding solvent and do a hot filtration before proceeding. To perform a hot filtration, fold a piece of filter paper into a fluted cone shape and place it into a glass stemless funnel. Add a 1020% excess of hot solvent to the hot solution to allow for evaporation in the procedure. Pour the solution through the paper. If crystals begin to form at any time during the process, add a small portion of warm solvent to dissolve them. Cooling the solution. Set the flask containing the dissolved compound on a surface that does not conduct the heat away too quickly, such as a paper towel set on a benchtop. Lightly cover the flask as it cools to prevent evaporation and to prevent dust from falling into the solution. Leave the flask undisturbed until it cools to room temperature. Once the crystals have formed, place the solution in an ice bath to ensure that the maximum amount of crystals is obtained. The solution should be left undisturbed in the ice bath for 30 minutes to 1 hatch, or till the compound appears to have completely crystallized out of solution. If no crystal formation is evident, it can be induced by scratching the inside walls of the flask with a glass rod or by adding a small seed crystal of the same compound. If this still fails to work, then too much solvent was probably used. Reheat the solution, allow some of the solvent to boil off, and then cool it, isolating and drying the crystals. Set the cold flask containing the newly formed crystals on a benchtop. Lightly cover the flask to prevent evaporation and to prevent dust from falling into the solution. Isolate the crystals by vacuum filtration, using either a Bickner or Hirsch funnel. Clamp the flask to a ring stand first. Rinse the crystals on the Bickner funnel with a small amount of fresh, cold solvent, the same solvent used for recrystallization, to remove any impurities that may be sticking to the crystals. To dry the crystals, leave them in the filter funnel and draw air through them for several minutes. Crystals can also be air-dried by allowing them to stand uncovered for several hours or days. More efficient methods include vacuum drying or placing in a desiccator. Polar solvent ethyl acetate methanol, water toluene less polar solvent hexane, methylene chloride ethanol hexane. Result: